Welcome to Gravity Science. I'm really glad you're here tonight. Before we begin our journey, tell me, where in the world are you listening from? Maybe you're resting in a quiet room, traveling softly on a late night train, or wrapped in a warm blanket with your favorite drink. Wherever you are, I hope this moment feels peaceful, safe, and ready to carry your mind into gentle wonder. Tonight, we're going to drift together toward a distant world, a place so far from the warmth of our sun that sunlight arrives there not as a blazing torch but as a whisper, a pale blue suggestion of radiance that takes more than 2.5 hours to complete its journey across the solar system. This world spins in the outer darkness, in the cold theatre of space where ice becomes stone and atmospheres swirl with gases that would freeze solid here on Earth. This world is Uranus, the 7th planet from our sun. And yes, we'll talk about the name, about the laughter it inspires, about the unfortunate accident of pronunciation that has made this magnificent celestial body the subject of countless jokes. But more than that, we'll explore the profound strangeness of this world, the way it rolls through space like a cosmic marble, knocked sideways by some ancient collision, the way its moons orbit in a configuration unlike anything else we know, the way it challenges everything we thought we understood about how planets should behave. Let your body settle deeper into whatever surface supports you now. Feel the weight of your head against the pillow, the gentle pressure of blankets or sheets against your skin, the way your breathing has already begun to slow, to deepen, to match the rhythm of these words as they arrive in your mind like waves arriving on a distant shore. You don't need to do anything right now except listen, except drift, except allow your thoughts to wander outward into the solar system, past Mars with its rusty deserts, past the asteroid belt with its tumbling rocks, past Jupiter with its great red storm, past Saturn with its impossible rings, and onward into the blue-green darkness where Uranus waits. The name itself is worth pausing over, worth understanding because it carries within it layers of history and mythology and pure linguistic accident. Uranus was the only planet in our solar system not named for a Roman god. All the others, Mercury and Venus and Mars and Jupiter and Saturn, carry Roman names, echoes of an empire that looked up at the night sky and saw reflections of their pantheon moving against the stars. But when William Herschel discovered this new world in 1781, peering through his telescope from his garden in Bath, England, he initially wanted to name it Georgium Sidus, George's star, in honour of King George III. Imagine that for a moment. Imagine a solar system where we counted off the planets and said Mercury, Venus, Earth, Mars, Jupiter, Saturn, George. The astronomy community resisted this naming convention, this intrusion of contemporary politics into the timeless realm of celestial mechanics. Instead, they reached further back into Greek mythology rather than Roman and selected Uranus, the primordial god of the sky, the father of the Titans, the original deity who personified the heavens themselves before being overthrown by his son Cronus, whom the Romans called Saturn. So the lineage makes a certain poetic sense. Saturn, named for the father of Jupiter, orbits inside the orbit of Uranus, named for the father of Saturn. The generations align. The mythology follows the architecture of the solar system outward from the sun, but the Greek name Uranus became Latinized to Uranus, and when English speakers tried to pronounce this Latinized Greek name, they settled, unfortunately, on a pronunciation that sounds identical to a phrase describing a part of human anatomy, Uranus. And thus began centuries of snickering, of childish jokes, of middle school students giggling in science class, of adults struggling to keep straight faces during planetarium presentations. Astronomers have tried various workarounds. Some pronounce it Uranus, with the emphasis on the first syllable, trying to create distance from the unfortunate alternative. Some say Uranus, attempting to return closer to the Greek original. Some simply avoid saying the name aloud whenever possible, referring instead to the 7th planet, or the ice giant, or using technical designations. But the jokes persist, the discomfort lingers, And this magnificent world, this strange sideways wonder of the outer solar system, remains trapped behind a name that makes people laugh for all the wrong reasons. And yet, and this is important, this is worth holding in your mind as you drift towards sleep, the name matters far less than the reality. The reality of Uranus is so strange, so beautiful, so fundamentally unlike anything else in our solar system that it transcends the accidents of human language. Let the name fade, let the jokes dissolve, let yourself instead imagine what it would actually mean to approach this world, to see it not as a word on a page or a source of humour, but as a place, as an actual sphere of matter and energy and motion existing in the vast cold reaches of space. You're travelling now, in your mind, outward from Earth. You've left behind the inner solar system with its rocky planets, its warmth, its relative proximity to the Sun. You've passed through the asteroid belt, that ring of debris left over from the formation of the solar system, millions of rocks tumbling in their orbits, ranging from grains of sand to mountains floating in space. You've swept past Jupiter, that gas giant so massive it contains more than twice the mass of all the other planets combined. Its gravity so strong it acts as a cosmic shield for the inner solar system, deflecting comets and asteroids that might otherwise rain down on Earth. You've glided past Saturn, pausing perhaps to admire those rings, those impossible thin disks of ice and rock, orbiting in perfect synchronized precision, each particle following its own path, yet creating from chaos a structure of breathtaking order and beauty. And now you're entering the realm of the ice giants. This is what astronomers call Uranus and Neptune, distinguishing them from the gas giants Jupiter and Saturn. The difference might seem subtle at first. All four are massive worlds without solid surfaces. All four are composed primarily of materials that exist as gases at room temperature on Earth. But the ice giants have a different internal structure, a different composition, a different relationship between their rocky cores and their outer atmospheres. Where Jupiter and Saturn are mostly hydrogen and helium, the primordial stuff of the universe, the ice giants have relatively more of what astronomers call ices, which in this context doesn't necessarily mean frozen water, but rather materials like water, methane, and ammonia that exist in various states depending on temperature and pressure. As you approach Uranus, the first thing you notice is the colour. It's blue-green, a pale aquamarine shade, unlike anything else in the solar system. This colour comes from methane in the planet's upper atmosphere. Methane molecules absorb red light but reflect blue and green wavelengths, and so when sunlight strikes the atmosphere of Uranus, the red portions of the spectrum are absorbed, trapped, converted to heat, while the blue and green portions bounce back out into space, carrying with them the visual signature of this distant world. It's a cold colour, an icy colour, a colour that speaks of distances and frozen gases and temperatures that would kill any Earth organism instantly. But approach closer and you begin to notice something profoundly strange, something that sets Uranus apart from every other planet we know. The axis of rotation is wrong. Every planet spins, rotating around an axis that runs through its poles. And as planets orbit the Sun, these axes generally point in roughly the same direction, tilted at various angles, but maintaining an approximate alignment. Earth's axis tilts about 23.5 degrees from perpendicular to its orbital plane, which gives us our seasons as different hemispheres tilt toward or away from the Sun during our yearly journey. Mars has a similar tilt. Jupiter and Saturn spin almost upright, but Uranus lies on its side. Its axis of rotation tilts 98 degrees, which means it essentially rolls around the Sun like a ball rolling along a track rather than spinning like a top. Let that image settle into your mind as you feel your own body growing heavier, more relaxed, more ready to surrender to sleep. Imagine a planet rolling sideways through space. Imagine what that means for its seasons, for the way sunlight falls on its surface. For most planets, the equator receives the most direct sunlight, the poles receive light at an angle, and as the planet orbits, all regions experience variations in illumination. But on Uranus, with its sideways tilt, the poles point almost directly at the Sun during portions of its orbit. The Uranian year lasts 84 Earth years. That's how long it takes this distant world to complete one full orbit around the Sun. And during this long, slow journey, each hemisphere experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. Imagine that. Imagine living on Uranus, if such a thing were possible, and watching the Sun circle around the horizon for 42 years, never rising, never setting, just spiraling around the sky in an endless day. And then, as your hemisphere finally rotates away from the Sun, imagine 42 years of night, of darkness, of seeing stars wheel overhead, but never seeing the Sun rise. The rotation period of Uranus itself, the length of its day, is about 17 hours and 14 minutes. So during those 42 Earth years of continuous sunlight, you would experience about 22,000 individual days, each one blending into the next without any distinction between day and night. Time would lose its ordinary meaning, the cycle of sunrise and sunset that governs so much of life on Earth, that sets our circadian rhythms, that divides our experience into manageable units, would simply not exist. You would have to develop an entirely different relationship with time, with cycles, with the passage of moments. But of course, you could not actually live on Uranus, could not stand on its surface, because it has no surface to stand on. Like all the outer planets, Uranus is a world without solid ground. If you could somehow survive the cold, survive the pressure, survive the lack of oxygen, and descend into the planet in a spacecraft, you would simply sink deeper and deeper through layers of gas that gradually become thicker, denser, hotter, transitioning from a thin outer atmosphere to a compressed fluid, to a supercritical state where the distinction between gas and liquid breaks down entirely, until finally, somewhere deep in the interior, you might reach a rocky core. The atmosphere you would pass through first extends for thousands of kilometers, composed primarily of hydrogen and helium, with that crucial addition of methane that gives the planet its color. The temperature in the upper atmosphere hovers around -224 degrees Celsius, cold enough that methane can condense into crystals, forming high-altitude hazes and clouds. Deeper down, the pressure increases, the temperature rises, and you enter the mantle, a thick layer perhaps 8,000 kilometers deep, composed of water, methane, and ammonia, existing in exotic states unknown on Earth. At the pressures and temperatures deep within Uranus, these simple molecules behave in strange ways. Water, that familiar substance that we drink and swim in and watch fall from the sky as rain, becomes something else entirely. It remains liquid far above its normal boiling point because the pressure prevents it from evaporating. It conducts electricity even though pure water is an insulator, because the extreme conditions break some of the molecular bonds, freeing ions to carry current. It's called an ionic ocean, and it may be part of why Uranus has such an unusual magnetic field. Let your breathing slow even more now. Let each exhalation carry away a bit of tension, a bit of the day's concerns, a bit of the need to stay alert. You're safe here, drifting through descriptions of a world so far away that its existence poses no danger, offers no demands, simply invites contemplation and wonder. The magnetic field of Uranus is indeed strange, twisted, unlike the relatively neat dipolar fields of Earth and Jupiter. On Earth, our magnetic field emerges from the motion of molten iron in our outer core, and it aligns roughly with our axis of rotation. The magnetic North Pole sits near the geographic North Pole. Compasses point north because north is where the magnetic field lines converge. But on Uranus, the magnetic field is tilted 59 degrees away from the axis of rotation and offset from the center of the planet. Instead of emerging from a deep core, it seems to be generated in that ionic mantle, in the flow and circulation of electrically conductive fluids in the outer regions of the planet. This creates a magnetic field that tumbles and wobbles as the planet rotates, that changes orientation dramatically over the course of a Uranian day, that creates a magnetosphere, a bubble of magnetic influence around the planet, shaped like nothing else we've encountered. When NASA's Voyager 2 spacecraft flew past Uranus in January of 1986, It was the first and so far only spacecraft to visit this distant world. The images it sent back revolutionized our understanding, transforming Uranus from a fuzzy blue-green disk visible only through telescopes into a real place with detail and structure and moons and rings. Before Voyager, we knew Uranus had 5 moons, named for characters from Shakespeare and Alexander Pope: Miranda, Ariel, Umbriel, Titania, and Oberon. Voyager discovered 10 more, small irregular moons orbiting in the same strange equatorial plane, dictated by the planet's sideways tilt. All of these moons orbit around Uranus's equator, which, because of the planet's tilt, means they orbit perpendicular to the ecliptic, the plane in which most solar system objects move. Imagine that configuration, that entire system knocked on its side, moons circling around the planet's middle, while the planet itself rolls along its orbital path. The moons experience the same extreme seasons as the planet, 42-year days and 42-year nights. Though being solid worlds with no or very thin atmospheres, they don't retain heat, the way a gas giant might, so they cycle through incredible temperature extremes. Miranda, the smallest of the 5 major moons, might be the strangest geological body in the entire solar system. When Voyager 2 flew past and photographed its surface, scientists were astonished by what they saw. The moon appeared to be a jumble of completely different terrains smashed together, as if several different worlds had been broken into pieces and then reassembled at random. There were ancient, heavily cratered regions. There were grooved, ridged areas that looked like nothing else in the solar system. There were massive cliffs, including Verona Rupes, a scarp that drops 5 to 10 kilometers straight down, making it perhaps the tallest known cliff in the solar system. Several theories attempt to explain Miranda's bizarre appearance. Perhaps the moon was shattered by an impact early in its history, broken into large fragments that then reaccreted, falling back together under their mutual gravity, but not quite reassembling into the same configuration. Perhaps tidal heating from gravitational interactions with Uranus and the other moons caused partial melting and resurfacing at different times. Perhaps we're seeing different stages of geological evolution frozen in place, preserved in the cold vacuum of space. We don't know for certain. Miranda remains a puzzle, a mystery, a reminder that even when we can photograph a world, even when we can see its surface in detail, we may still struggle to understand how it came to be the way it is. Feel your eyelids growing heavier now, if they're not already closed. Feel the way your mind can hold these images, these descriptions, without effort, without strain. You don't need to memorize anything, don't need to remember specific facts or figures. You're simply allowing yourself to drift alongside the information, to let it wash over you like waves, like the slow rhythm of breathing, like the gentle pull of gravity that keeps moons orbiting planets and planets orbiting stars. Uranus also has rings, though they are nothing like Saturn's glorious bright bands. The rings of Uranus are dark, narrow, and composed of particles that reflect very little light. They were discovered in 1977, not by direct observation, but by watching what happened when Uranus passed in front of a star. Astronomers were hoping to observe the starlight passing through Uranus's atmosphere, which would tell them about the atmosphere's composition and structure. But before the planet itself blocked the starlight blinked off and on several times in a pattern too regular to be random. Something was orbiting Uranus, something that blocked the starlight in a series of narrow bands. The rings. Voyager 2's cameras later imaged these rings directly, revealing 13 distinct rings, ranging from less than a kilometer to a few kilometers wide. The particles that compose them are dark, perhaps, coated with radiation, processed organic compounds, perhaps composed of material that formed far from the sun, where ice is mixed with carbonaceous dust. The rings are young by solar system standards, perhaps only a few 100 million years old, possibly the remnants of a small moon that was shattered by an impact, or torn apart by tidal forces when it ventured too close to the planet. Everything about Uranus seems to speak of violence, of disruption, of a history that did not unfold smoothly. That sideways tilt, that 98-degree axial tilt that makes the planet roll through space, almost certainly resulted from a massive collision early in the solar system's history. The leading theory suggests that during the chaotic period of planetary formation, when the solar system was still crowded with planet-sized bodies jostling for position, colliding, merging, being flung into new orbits by gravitational interactions, Uranus was struck by an Earth mass or larger object. The impact was so violent that it knocked the entire planet onto its side. Think about the scale of that collision. Think about what it would mean for something as massive as Earth to slam into a planet much larger than Earth at speeds measured in kilometers per second. The energy release would be beyond comprehension, enough to vaporize the impactor, to liquefy portions of Uranus, to send shockwaves through the planet's interior that might still be affecting its internal structure billions of years later. And yet the planet survived. It didn't shatter, it didn't break apart. It absorbed the impact, reorganized, settled into a new configuration, and continued its orbit around the Sun, tilted now at an angle that makes it unique among the planets. This violence, this history of impact and disruption, might also explain why Uranus is so cold. Of all the giant planets, Uranus emits the least heat from its interior. Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, releasing the heat left over from their formation, plus additional heat generated by gravitational contraction, and, in Jupiter's case, the precipitation of helium rain deep in the atmosphere. But Uranus barely radiates any excess heat. Its effective temperature, the temperature we measure based on its thermal emission, is almost exactly what we would expect from a body simply absorbing and re-radiating sunlight, with no internal heat source. Why is Uranus so cold inside? Well, one possibility is that the giant impact that tipped the planet on its side also disrupted the normal convection patterns that would carry heat from the deep interior to the surface. Perhaps the impact mixed the interior in a way that prevented the normal stratification, the normal separation of materials by density that drives convective circulation. Perhaps heat is trapped deep inside, unable to reach the surface. Or perhaps Uranus simply formed differently, with less residual heat to begin with, though this seems less likely given that Neptune, which formed in a similar location and should have a similar history, does emit substantial excess heat. These are the kinds of questions that keep planetary scientists awake at night and that may gently carry you towards sleep. These unanswered puzzles about worlds so distant that we've only visited one of them once, briefly, as a spacecraft hurtled past at tens of thousands of kilometers per hour. Everything we know about Uranus comes from that single flyby in 1986 and from ongoing observations with Earth-based and space-based telescopes. We've been watching Uranus for nearly 2.5 centuries now, since Herschel first noticed it moving against the background stars, and yet we still have only the barest understanding of its interior structure, its atmospheric dynamics, its magnetic field generation, the history and evolution of its ring and moon system. The atmosphere of Uranus presents its own mysteries. Unlike Jupiter and Saturn with their colourful bands and swirling storm and constantly changing features, Uranus appears remarkably bland in visible light. When Voyager 2 flew past, it saw almost no features at all, just a nearly uniform blue-green disk. Scientists initially thought Uranus might be a calm, quiet world, meteorologically speaking. But as telescope technology improved, as we developed the ability to observe in infrared wavelengths and to track subtle variations over time, we began to realize that Uranus does have weather, does have storms, does have atmospheric circulation, but it's all more subtle than on Jupiter or Saturn, harder to see, harder to track. Part of this may relate to the low internal heat. On Jupiter and Saturn, internal heat drives powerful convection, creating updrafts and downdrafts that organize into the bands and zones we can see from Earth. But on Uranus, with almost no internal heat source, the atmosphere is driven primarily by the tiny amount of sunlight that reaches it. And remember, sunlight at Uranus's distance is less than 1/400th as intense as sunlight at Earth. It's not much to work with, and yet the atmosphere does circulate, does develop features, does respond to seasonal changes as different hemispheres tilt toward or away from the Sun during the 84-year orbit. In 2007, Uranus reached equinox, a moment when the Sun crossed directly over the planet's equator. This happens twice per Uranian year, at intervals of 42 years. During equinox, instead of one pole being illuminated and one in darkness, the entire planet receives sunlight distributed more evenly from pole to pole, though still at the extreme distance that makes even noon on Uranus dimmer than twilight on Earth. Astronomers watched eagerly to see how the atmosphere would respond to this change in heating patterns, and they saw an outbreak of storm activity, bright spots appearing in the atmosphere, clouds forming and dissipating, circulation patterns shifting. These observations suggested that Uranus's atmosphere is more active than it appears, that beneath the bland exterior, dynamic processes are constantly at work, mixing gases, transporting heat, generating winds. The winds on Uranus can reach over 900 kilometers per hour in some regions, though they're generally slower than the winds on Neptune, which can exceed 2,000 kilometers per hour. The wind patterns follow the planet's rotation, circling around the axis in the same direction the planet spins, but with complex variations in speed at different latitudes. Let yourself sink deeper now, into rest, into the soft boundary between waking and sleep. Your breathing has found its own slow rhythm. Your muscles have released their tension. Your mind is following these words without effort, without concentration, simply receiving them like a landscape receiving moonlight, passively, gently, without need for response. The details of Uranus's atmospheric circulation, the specifics of its wind patterns and storm systems, can float through your awareness without demanding understanding, without requiring analysis. They're simply there, like stars in the night sky, points of light against the darkness. The moons of Uranus carry their own stories, their own mysteries. Beyond the 5 large classical moons discovered before the space age, Voyager 2 found 10 small inner moons, and subsequent observations from Earth-based telescopes and the Hubble Space Telescope have revealed additional outer irregular moons, bringing the total known count to 27. Each one is named for a character from Shakespeare or Alexander Pope, maintaining a literary theme unique among planetary moon systems. Jupiter's moons are named for Zeus's lovers, Saturn's for Titans and other mythological figures, but Uranus's moons bear names like Juliet, Desdemona, Cordelia, Ophelia, Puck. Ariel, one of the 5 major moons, shows evidence of past geological activity. Its surface is crossed by long valleys and fault scarps, suggesting that something caused the moon to expand or contract, fracturing the ice crust. Perhaps tidal heating from gravitational interactions with Uranus and the other moons partially melted the interior, allowing the moon to expand. Perhaps radioactive decay in the rocky core generated heat over long periods. Perhaps both processes contributed. The surface also shows signs of resurfacing, with some regions appearing much younger than others, suggesting that geological activity may have continued episodically over much of the moon's history. Umbriel, in contrast, appears ancient and dead. Its surface is heavily cratered, dark, and shows little sign of geological modification since its formation. It's the darkest of the large Uranian moons, reflecting only about half as much light as Ariel. No one knows quite why. Perhaps its surface composition is different. Perhaps it lacks whatever resurfacing processes smoothed over craters on the other moons. There's a curious bright ring near one pole, a crater or depression called Wunder that stands out as the brightest feature on the moon. But otherwise, Umbriel is a dark, ancient, unchanging world. Titania is the largest of Uranus's moons, about half the diameter of our own moon. Its surface shows a mix of cratering and tectonic features, including an enormous canyon system called Messina Chasma that cuts across the surface for over 1,500 kilometers. Something pulled Titania's crust apart, creating this vast crack in the ice. Perhaps the moon's interior froze and expanded, stretching the surface. Perhaps tidal forces from Uranus stressed the crust beyond its breaking point. The canyon is ancient now, cold, airless, its walls standing stark against the black sky, unmarked by erosion because there is no atmosphere, no wind, no water to wear them down. Oberon, the outermost of the 5 major moons, also shows signs of past activity mixed with ancient, heavily cratered terrain. One mountain on Oberon rises about 11 kilometers above the surrounding surface, a peak of water ice jutting into space, surrounded by impact craters and fault lines. Like all the Uranian moons, Oberon is a strange hybrid world, made primarily of water ice mixed with rock, hard as stone in the extreme cold, but fundamentally different from the rocky worlds of the inner solar system. And then there is Miranda, which we've already touched upon, but which deserves more attention because it is so genuinely strange. The moon is only about 500 kilometers in diameter, small enough that if you stood on its surface, you could see the curvature of the horizon easily, could throw a rock hard enough that it might escape the moon's weak gravity entirely and drift off into space. And yet, despite its small size, Miranda's surface displays an incredible diversity of features crammed into a limited area. There are regions called coronae, strange oval-shaped features with complex internal patterns of ridges and grooves. There are plains, there are cliffs, there are ancient cratered highlands. Everything seems to be jumbled together as if the moon is a collage, a scrapbook of different geological processes that somehow all occurred on the same small world. The leading explanation remains that Miranda was catastrophically disrupted, shattered by an impact, and then reassembled. But the details remain unclear. How many pieces did it break into? How long did reassembly take? Did some of the fragments melt during the impact, creating the strange grooved terrains as they solidified? We may not know the answers until we send another spacecraft to Uranus, and such a mission remains decades away at best. The outer solar system is so vast, the travel times so long, the technical challenges so significant, that missions to the ice giants receive lower priority than missions to Mars or the moons of Jupiter and Saturn, worlds that are closer, easier to reach, potentially more relevant to the search for life. But there is a growing movement among planetary scientists to prioritize a return to Uranus, to send an orbiter that could spend years studying the planet, its rings, its moons, its magnetic field, its atmospheric circulation, all the aspects that we glimpsed only briefly during Voyager's flyby. Such a mission might launch in the 2030s and arrive in the 2040s using gravity assist from Jupiter to speed the journey. It would carry cameras and spectrometers and magnetometers and radar, instruments to map the moons in detail, to probe the atmosphere, to measure the planet's gravitational field, and thereby learn about its interior structure. It might carry a probe to drop into the atmosphere, descending through the cloud layers, measuring temperature and pressure and composition as it falls, transmitting data until the increasing pressure crushes it, or the cold freezes its systems, or the signal can no longer reach the orbiter overhead. Imagine the images such a mission might return. Imagine watching clouds swirl in Uranus's atmosphere in real time, tracking storms as they develop and evolve. Imagine close-up views of Miranda's cliffs and Ariel's valleys and Titania's canyons, details sharp enough to see individual boulders, to trace the patterns of ancient ice flows, to count the small craters that pepper every surface in the solar system. Imagine the discoveries that might emerge, the answers to questions we don't even know to ask yet. But even without new missions, even with only the data we have now, Uranus teaches us profound lessons about the nature of planets, about the diversity of worlds that exist even within our own solar system. For most of human history, we knew only one planet intimately, Earth. We could observe the others as points of light in the sky, could track their motions, could eventually resolve them into disks through telescopes. But we had no way to know what they were actually like. Were they solid, gaseous, hot, cold? Did they have weather, moons, rings? The space age changed everything. We sent robots to these distant worlds, and they sent back images and data that revealed each planet as a unique place with its own character, its own history, its own rules. Mars, with its extinct volcanoes and frozen water and ancient river valleys, speaks of a time when it might have been warm and wet. Venus, hidden beneath clouds of sulfuric acid, shows us what happens when a greenhouse effect runs away. when carbon dioxide accumulates in an atmosphere until the surface becomes hot enough to melt lead. Jupiter, with its enormous magnetosphere and dozens of moons, is almost a miniature solar system unto itself. Saturn's rings demonstrate principles of orbital mechanics and particle dynamics in beautiful visual form. And Uranus, with its sideways spin and cold interior and strange magnetic field, shows us that planets can be knocked onto their sides and survive. That the solar system's history was more violent than we might imagine. That worlds can experience seasons lasting decades. That nature is endlessly creative in the ways it arranges matter and energy. There is no single template for how a planet must be. There is no standard configuration. Each world is the product of its particular history, the sum of all the events, collisions, interactions, and processes that have shaped it since its formation. Your mind is wandering now, perhaps? Drifting between the words and your own thoughts, your own dreams, the images and sensations that arise spontaneously at the edge of sleep. That's exactly right. That's exactly where you should be. You don't need to follow every detail, don't need to track the progression of ideas. You can simply float alongside them, can let them be present without demanding your attention. The story of Uranus, the science of its formation and structure and behavior, continues whether you're fully conscious of it or not, continues like the planet itself, continues to orbit through space, indifferent to observation, existing in its own right. The formation of Uranus began 4.5 billion years ago in a disk of gas and dust orbiting the young sun. This disk, called the solar nebula, contained all the raw material that would eventually condense into planets, moons, asteroids, comets, everything in the solar system. Close to the sun, where temperatures were high, only materials like rock and metal could condense into solid particles. Further out, beyond what's called the frost line, water ice could also condense, and still further out, methane and ammonia and other volatile compounds could freeze. Uranus formed in this outer region, in the cold reaches of the solar nebula, where ices were abundant. The process began with tiny particles of dust and ice colliding and sticking together, gradually building up larger and larger clumps. These clumps, called planetesimals, range from meters to kilometers across. As they grew, their gravity increased, allowing them to attract additional material more efficiently. The largest planetesimals grew into planetary embryos, bodies perhaps the size of Mars or Earth, and these embryos continued to sweep up material from their orbital zones. At some point, a planetary embryo in Uranus's region of the solar nebula became massive enough to start capturing gas directly from the nebula, accreting not just solid material but also hydrogen and helium. This process created the atmosphere and probably the outer layers of the planet. But unlike Jupiter and Saturn, which formed closer to the Sun where the nebula was denser and more material was available, Uranus never became a true gas giant. It accumulated a substantial envelope of hydrogen and helium, but the majority of its mass remained in the form of ices and rock. The timing of Uranus's formation, relative to the lifetime of the solar nebula, may have been crucial. The nebula didn't last forever. Within a few million years, the young sun became active, generating powerful stellar winds that blew away the remaining gas, leaving behind only the solid material that had already been incorporated into planets and smaller bodies. If Uranus was still in the process of accreting gas when the nebula dispersed, it would have been frozen in an intermediate state, more massive than a terrestrial planet, but less massive than a gas giant, an ice giant. After the nebula dispersed, the young solar system was still crowded with debris, with planetesimals that hadn't been incorporated into planets, with planetary embryos that were still migrating, still interacting gravitationally, still occasionally colliding. This was the era of the late heavy bombardment, a period of intense impacts throughout the inner solar system, and it was probably during this chaotic time that Uranus suffered the collision that tipped it on its side. Imagine the solar system 4 billion years ago, still settling into its final configuration. Planets moving in orbits that weren't quite stable yet. Large bodies drifting, being scattered by gravitational interactions with Jupiter and Saturn, occasionally crossing paths. And then imagine two of these bodies, one of them Uranus, the other a planet-sized object whose name we'll never know because it no longer exists, approaching each other on a collision course. They would have been moving at orbital velocities, kilometers per second, and when they collided, the impact would have released as much energy as billions of nuclear weapons detonating simultaneously. The impactor would have been destroyed instantly, vaporized, its material mixing with Uranus's outer layers. Shockwaves would have propagated through Uranus's interior, compressing material, generating heat, potentially disrupting whatever internal structure had begun to form. And the planet's spin axis would have been knocked sideways, torqued by the off-center impact, tipped over until it lay almost in the plane of its orbit. The planet's moons, if any existed at that time, might have been destroyed or flung away. The current moon system might have formed later, condensing from a disk of debris left over from the impact, which would explain why all the moons orbit in Uranus's equatorial plane, aligned with the new tilted axis rather than with the planet's original orientation. This is of course theoretical. We weren't there to observe it, we can't rewind time and watch what actually happened. But it's the best explanation we have for Uranus's unique properties, and it's consistent with what we know about the early solar system's violent history. Impact craters cover almost every solid surface in the solar system. The Moon's giant impact basins, Mercury's huge Caloris basin, Mars's Hellas planitia, all testify to a time when large impacts were common. Earth itself probably suffered a giant impact that ejected the material that formed our moon. Collisions were not aberrations. They were a normal part of planetary formation. Let your body relax even more deeply now. Let go of any remaining tension in your shoulders, your jaw, your forehead. Let your eyes rest gently behind closed lids. Let your awareness of your physical surroundings fade a little more. You're suspended in a state between waking and sleeping, a state where information can arrive without demanding analysis, where images can form without requiring interpretation. The story of Uranus, the story of its formation and collision and long, slow orbit through the outer solar system, is also a story about time, about the deep time of planetary evolution, about changes that occur over billions of years. It's almost impossible to truly grasp that timescale. Human lifetimes are measured in decades. Civilizations rise and fall over centuries or millennia. All of recorded human history spans only about 5,000 years. The oldest known rocks on Earth are about 4 billion years old, and they've been transformed by heat and pressure and geological processes until they bear little resemblance to the rocks that first solidified from molten magma. But Uranus has been orbiting the Sun for 4.5 billion years, has completed more than 50 million orbits, has experienced billions of those 84-year-long great years, each one divided into its strange seasons of light and darkness. And throughout all that time, the planet has been slowly changing, slowly evolving. Its interior has been cooling, though, as we've noted, it never had as much internal heat as the larger gas giants. Its atmosphere has been mixing, with lighter gases gradually floating upward and heavier materials sinking. Its magnetic field has been churning, driven by motions in the Ionic Ocean deep in the mantle. Its moons have been migrating, their orbits slowly shifting due to tidal interactions. Tiny particles have been continually bombarded by micrometeorites, by radiation from the sun and from cosmic rays, slowly eroding surfaces, darkening materials through radiation processing. Nothing in the solar system is truly static. Everything is in motion, everything is changing, though many of the changes occur so slowly that they're invisible on human timescales. Uranus is rolling around the Sun right now, at this very moment, moving at about 6.8 kilometers per second in its orbit. Its atmosphere is circulating. Its magnetic field is rotating and wobbling. Particles in its rings are colliding and fragmenting. Ice volcanoes on its moons, if they exist, might be slowly releasing water vapor into space. All of this is happening in the darkness at the edge of the solar system, whether we observe it or not, whether we think about it or not. And in another sense, Uranus is also travelling through the galaxy. With the Sun and all the other planets, the entire solar system orbits the centre of the Milky Way galaxy at a speed of about 220 kilometers per second, completing one full galactic orbit every 230 million years. In the time since Uranus formed, the solar system has completed about 20 orbits around the galaxy. We've circled through different regions of the galactic disk, have passed through spiral arms where star formation is active and supernovae are common, have traversed quieter regions between the arms. The flux of cosmic rays has varied, the density of interstellar material has changed, and through it all, Uranus has continued its own local orbit around the Sun, indifferent to the larger cosmic motions. This nested structure of motions, this hierarchy of scales, is one of the profound insights of astronomy. Uranus spins on its axis every 17 hours. It orbits the Sun every 84 years. It circles the galaxy every 230 million years. And the galaxy itself is moving through intergalactic space, part of a local group of galaxies that includes the Milky Way and Andromeda, and several dozen smaller galaxies, all of which are drifting through the universe, being pulled by the gravity of massive galaxy clusters, participating in the large-scale structure of the cosmos. But let's return to the more immediate scale, the scale of the planet itself, the scale where human spacecraft might someday travel. If we did send a probe to Uranus, if we committed the resources and time necessary to mount such a mission, what might we learn? What questions might we answer? The list is long. We would want to understand the planet's interior structure in detail. How large is the rocky core? What is the exact composition of the mantle? Where is the magnetic field generated, and why is it so offset and tilted? Is there truly very little internal heat, or is heat somehow trapped deep inside? We would want to study the atmosphere comprehensively. What drives the circulation patterns? How do storms form and evolve? What is the vertical structure of the atmosphere? Are there multiple cloud layers? What is the detailed composition, including trace gases, that might tell us about chemical processes occurring in the atmosphere? How does the atmosphere respond to the extreme seasonal variations as different hemispheres experience their 42-year days and nights? We would want to map the moons in high resolution. What is the exact composition of each moon's surface? How thick is the ice crust? Is there liquid water beneath the ice on any of them? What internal structure do the moons have? What caused the tectonic features we see? How old are the different surface regions? Are any of the moons geologically active today? We would want to understand the ring system in detail. What is the size distribution of particles in the rings? Why are they so dark? How old are they? Where did they come from? Why are they so narrow and well defined when Saturn's rings are broad and diffuse? Are there shepherd moons, small moons whose gravity confines the ring particles to narrow bands? How long will the rings last before being dispersed? We would want to measure the radiation environment around Uranus. The planet's magnetosphere, twisted and wobbling as it is, traps charged particles from the solar wind, creating radiation belts somewhat analogous to Earth's Van Allen belts. How intense is the radiation? How does it vary with the planet's rotation? How does it affect the surfaces of the inner moons and the ring particles? And beyond all these specific scientific questions, there's a more general motivation for exploring Uranus. The simple human desire to see new places, to extend our reach, to understand the full diversity of our cosmic neighborhood. We are, as a species, curious. We wonder what lies beyond the horizon. We build vehicles and instruments to extend our senses. We send robots to places too distant or dangerous for humans to travel. And we learn. The knowledge we gain from studying Uranus isn't immediately practical. It won't cure diseases or solve climate change or feed hungry people. But it enriches our understanding of how planetary systems work, of how worlds form and evolve, of what kinds of places exist in the universe. And that understanding, over time, feeds back into practical concerns. The same physics that governs the circulation of Uranus's atmosphere also governs Earth's atmosphere. The same principles of planetary formation that explain Uranus's composition also help us understand Earth's history. The same techniques we develop for analyzing data from distant spacecraft also have applications in medical imaging, resource exploration, environmental monitoring, and beyond even the practical spin-offs, there's something deeply meaningful about simply knowing more about the universe we inhabit. We are not separate from the cosmos. We are part of it, made of the same elements, governed by the same physical laws, participating in the same great unfolding story of matter and energy. When we study Uranus, we're studying ourselves in a sense, examining one particular outcome of the processes that shape worlds, one branch of the great tree of planetary possibilities. Your breathing is very slow now, very deep, very regular. You might already be more asleep than awake, drifting in and out of consciousness, the words arriving like sounds heard from a great distance. Meaningful yet dreamy. That's good. That's exactly right. There's nothing you need to do, nowhere you need to be, no task that requires your attention. Just rest. Just let the story of Uranus continue to unspool, a gentle stream of words and images carrying you toward sleep. The name, the unfortunate name, seems less important now, doesn't it? When you understand what Uranus actually is, when you can picture it rolling through space in the darkness beyond Saturn, when you know something of its history and structure and moons, the jokes fade away. They become irrelevant. The reality is so much more interesting than the juvenile humour. Yes, the name is awkward. Yes, it's unfortunate that English pronunciation creates that particular sound. But the planet itself transcends the name, exists independent of what we call it, indifferent to our linguistic accidents. In a few billion years, the sun will begin to die. It will exhaust the hydrogen in its core and start fusing helium, swelling into a red giant, its outer layers expanding perhaps as far as Earth's orbit. The inner planets will be incinerated, Mercury and Venus certainly, possibly Earth as well. But Uranus, far out in the cold reaches of the solar system, will survive. The increased solar luminosity might even warm it slightly, might drive more active weather in its atmosphere, might cause some of the ice on its moons to sublimate into space. But fundamentally, Uranus will remain, will continue its orbit around the dying sun, patient, enduring, unchanged in any essential way. Eventually, the sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf, a dense stellar core slowly cooling over trillions of years. Uranus will orbit this white dwarf, receiving almost no heat, almost no light, becoming even colder than it is now. Its atmosphere might freeze, might condense into a solid shell covering the planet. Its moons will become darker than night, lit only by starlight, and still the planet will continue. Still it will roll through space, preserving in its tilted axis the memory of that ancient collision, that moment of violence that set it on its unique path. And billions of years after that, long after the sun has cooled completely, long after the last stars in the universe have died, Uranus might still exist, a frozen relic of a cosmos that once was warm, once was bright, once was filled with energy and light. Or perhaps before then, it will be ejected from the solar system by a gravitational interaction with a passing star, flung out into interstellar space to wander forever through the dark between galaxies, a rogue planet carrying its moons and rings with it, a complete self-contained system drifting through the cosmic void. These futures are speculative, of course. We can't know exactly what will happen over such vast timescales. Other events might intervene. Galaxies collide and merge. The Milky Way will merge with Andromeda in a few billion years, and during that merger, stellar orbits will be scrambled, solar systems might be disrupted. The universe itself might end in a big crunch, or a big rip, or a heat death, depending on which cosmological model proves correct. But for now, for the present moment, which is the only moment we ever truly inhabit, Uranus is there, orbiting, existing, being itself. And you are here, on Earth, perhaps now asleep, or very nearly so, your consciousness fading into dreams, your body resting, your mind releasing its grip on waking concerns. The distance between you and Uranus, the billions of kilometers of space, the emptiness and cold, is absolute. You will never go there, No human will ever stand on Uranus's non-existent surface or walk on its airless moons. The distances are too vast, the environment too hostile, the technology required too far beyond anything we currently have. But in another sense, you have been there tonight, in imagination, in thought, through the words that carried you outward into the solar system and showed you, in descriptions and images and scientific facts, what that distant world is like. This is the power of language, of storytelling, of science communicated with care and attention. We can transcend our physical limitations. We can extend our awareness across the solar system, across the galaxy, across the universe. We can understand, at least in part, places we can never visit, phenomena we can never experience directly, scales of time and space that dwarf human existence. We can know that Uranus takes 84 years to orbit the Sun, even though no human will ever live long enough to observe a complete Uranian year. We can know that it was knocked on its side by an ancient collision, even though no one was there to witness it, and no record exists except in the planet's current orientation. Science is, in this sense, a form of time travel and space travel, a way of reaching beyond our immediate sensory experience to grasp truths about the universe. And when science is shared through stories, through narratives that unfold slowly and gently, like this one, it becomes more than just a collection of facts. It becomes a way of seeing, a way of understanding our place in the cosmos, a source of wonder and humility and connection. You are very small, a single human body on a small planet, orbiting an ordinary star in an unremarkable galaxy. But you are also part of something vast, something ancient, something ongoing. The atoms in your body were forged in stellar cores, in supernovae that scattered their enriched material across space, material that was later incorporated into the solar nebula that formed the Sun and planets. You are made of star stuff, as Carl Sagan famously said. The same elements that compose Uranus compose you. The same physical laws that govern its orbit govern the biochemical processes that keep you alive. There is no separation, not really. The boundaries we perceive, between self and other, between Earth and space, between living and non-living, are useful distinctions for navigating daily life, but they're not fundamental. At the deepest level, everything is connected, everything is part of the same universe, the same unfolding pattern of matter and energy in space and time. Uranus is your distant cousin, a fellow product of the solar system's formation, shaped by the same processes that shaped Earth, obeying the same rules. And now, as you rest here in darkness or dim light, as your breathing continues its slow rhythm, as your mind drifts through dreams and half-conscious thoughts, Uranus is out there, rolling through space, silent, cold, patient, indifferent. It doesn't know you exist. It doesn't know anything, being an inanimate sphere of gas and ice and rock. But you know it exists, have spent this time learning about it, thinking about it, imagining it. And in that knowledge, in that attention, a connection is formed, a thread of awareness stretching from your mind across billions of kilometers to that distant world. This is perhaps the deepest meaning of exploration, of science, of the human drive to understand. We reach out with our instruments and our mathematics and our spacecraft, yes, but we also reach out with our minds, with our capacity for wonder and curiosity. We ask questions, we seek answers, we build models and theories to explain what we observe, we tell stories to share what we've learned, and in doing so, we transform the universe from a cold, meaningless void into a cosmos, an ordered whole, a place where everything connects to everything else, where understanding is possible, where meaning can be found. Uranus, the unfortunately named, the strangely tilted, the cold and distant ice giant, is part of that cosmos. It has its place in the grand structure, its role in the history of the solar system. It teaches us about planetary formation, about giant impacts, about atmospheric circulation in the absence of strong internal heating, about magnetic field generation, about ring systems, about moon formation. Every observation adds to our understanding. Every measurement refines our models. Every image reveals new details. And someday, perhaps in your lifetime, perhaps after you're gone, we'll send another spacecraft to Uranus. We'll watch it launch from Earth, a small package of metal and electronics and scientific instruments riding a column of fire into space. We'll track it as it travels outward, past the Moon, past Mars, past the asteroid belt. We'll watch it swing past Jupiter, using that giant planet's gravity to fling itself faster and farther out into the solar system. And then we'll wait, years passing, as the spacecraft coasts through the empty space between Jupiter and Uranus, travelling in silence, alone, carrying humanity's questions toward that distant world. And eventually, maybe 10 years after launch, maybe 15, the spacecraft will arrive. It will fire its engines to slow down, to be captured by Uranus's gravity, to settle into orbit around the planet, and then it will begin its work, photographing the atmosphere, measuring the magnetic field, mapping the moons, analysing the rings, collecting data continuously, transmitting it back to Earth, where scientists will analyse it, will publish papers, will gradually piece together a more complete understanding of this strange world. The images will be spectacular. We'll see clouds at Uranus's cloud tops in detail. We'll watch them move and evolve over time. We'll see the moons up close. We'll count craters. We'll measure surface compositions. We'll identify geological features we can't even imagine yet. We'll see the rings edge on and face on. We'll track individual particles. We'll understand their dynamics. We'll measure the wobbling of the magnetic field. We'll probe the interior using gravity measurements. We'll answer questions that have puzzled scientists for decades. And in the process, we'll surely discover new mysteries, new questions we never thought to ask. That's how science works. Every answer raises new questions. Every observation reveals phenomena we didn't expect. The universe is always more complex, more subtle, more interesting than our theories predict. Uranus will surprise us. It will show us things we never imagined. It will teach us lessons we didn't know we needed to learn. But all of that is in the future. For now, in this present moment, Uranus remains mostly mysterious, mostly unknown, a world we've glimpsed only briefly from a great distance. It keeps its secrets. It rolls through space in its unique way, experiencing its 42-year seasons, its 17-hour days, its 84-year orbit. It exists, solid and real and physical, out there in the darkness, waiting for us to return, to look more closely, to understand more deeply. And you, right now, are deeply relaxed, deeply at peace, perhaps already asleep. Your mind having followed this long winding journey from the name Uranus to its formation, from its atmosphere to its moons, from its strange tilt to its distant orbit, from the present moment to the far future billions of years hence. The story has served its purpose, has occupied your conscious mind while your body prepared itself for sleep, has given you something to think about that is interesting but not disturbing, complex but not demanding, distant but not irrelevant. The universe is vast beyond comprehension, filled with wonders we've barely begun to explore. Uranus is just one planet, one world among billions in the galaxy, one small piece of the cosmic puzzle. But it's our piece, part of our solar system, part of our local neighborhood. We can study it, we can learn from it, we can appreciate its strange beauty, its unique character, its role in the larger story of planetary formation and evolution. And as you slip fully into sleep now, as the words fade away and dreams take over, as your conscious mind releases its grip and allows unconscious processes to take control, perhaps some small part of your awareness will remain connected to Uranus. We'll remember that it's out there. We'll carry with it a sense of the vastness of space, the depth of time, the complexity and beauty of the universe we inhabit. Sleep well, rest deeply, dream of distant worlds, of ice and methane, of moons with strange names, of rings, circling in darkness, of a planet that rolls instead of spins, of 42-year seasons and 17-hour days, of a cosmos that is stranger and more wonderful than we can imagine, and of which you are an inseparable part. The universe continues, Uranus continues, your breathing continues, slow and steady, in and out, rising and falling like waves, like the tides, like the motion of planets through space, regular, reliable, eternal. Rest now, just rest. Let everything else go. Sleep.